First, I want to talk about next week. Next week will be our last week of the semester. Last week. And so today we finish Module 4. Then Wednesday we start Module 5. So we have two classes. Two classes. We need to cover, relatively small material from Module 5, but at the same time, we need to do some review for the final. Yeah, review for the final. Yeah. So I need to talk about your common errors in homework assignment number 2. Yeah. So I need to find. Let me about. 1 hour, about 1 hour. Yeah, about 1 hour I do review. Yeah, all right. But the next week, there is one important change I want to let you know here. Yeah. So next week, the final week. The final week, the first half, Monday's class, still regular class. Monday's class. But Wednesday's class, that's our final exam time. Wednesday, our class time, this time, okay? 2 hours period, that's your final time, all right? Yeah, so next week, Wednesday. But next week, I need to make some change. Yeah, so here I'm talking about, let me write here a little bit. So next week, that is our final week also. All right. This class, because we do it in the hybrid mode, right? One in person, one online, each week, 2 classes, right? So next week, I need to make switch. Next week, okay? Right. All right. Yeah. Let me write a date. So next week, Monday, right? August the 4th, Monday. Yeah. And the Wednesday, August 6th, Wednesday. This is our final exam time. Final exam time. Okay? All right. Yeah. But because I don't want you come to the classroom twice a week, right? Yeah. Once a week, not twice a week. And Wednesday you have to come to the classroom. Yeah. That's so we make the change. Monday's class, we make it online. So we swap Monday, our usual Monday, Wednesday, yeah, just for the last week, final. Okay, all right. So remember, Monday we do it online. Yeah, for most students, so they do online anyway. But for you too, yeah. So yeah, you do not need to come to the classroom on Monday. Yeah, but Wednesday everybody should come to the classroom. Okay, yeah. So, so come to the classroom. Same class, yeah. Oh, the classroom. Classroom, let's use this one. Yeah. In case I need to show you something, right? That projector, I couldn't show you anything. Yeah. Yeah, here, let me just, Bush Hall, 30,
0002.
yeah, 0, yeah, not 3, yeah, 002, yeah, yeah. this classroom, yeah, not 004, okay? Yeah, because the projector, we don't want to try it, yeah. It never works. So let's use 002, this classroom, yeah. In case if I need to show you some information, I can do it, yeah. All right. Yeah, but remember, I will also post announcement because some students, if they do not watch this video, I need to post announcement so let everybody know. So Monday's class online, Wednesday, yeah. So everyone, you need to come to the classroom, okay? Yeah. But I don't know if anyone, yeah, because sometimes some students may need to travel. It could happen. Some students, if you need to travel, you need to contact me as soon as possible. Yeah. In our final exam time, if you need to travel, so then I need to, make appointment with you, so we can do final through Zoom. Yeah. But only for those students with special situations. Yeah. Yeah. Other than that, I need to see you work in the classroom. Okay. Yeah. Yeah. All right. So that's the plan next week. Yeah. All right. Now, this topic, C.5, find second largest element. Yeah. So this solution, you need to do some work. Yeah. So this one, yeah, let me explain the details. Yeah. And after this one, the following next topic, we need to use result from this one. Yeah. So we need to understand this is special selection problem. Yeah. Second largest. Yeah. All right. So let's work on it. Yeah. The first time when we work, round one, we run the tournament method. Yeah. So we do this many, many times. Tournament method. Oh, just a minute. I saw two chat messages. Let me check if there is anything important I need to address. All right. So Michelle attending Wednesday, person not must. Yeah, I answered. Yeah. So yeah, it's a must, but students with special situation, yeah. So it's not optional for normal students, okay? But students with some very special situation, then I need to find some special way. Yeah, but I need to let you do the final, right? I cannot, just, for some special reasons, you couldn't do the final. Yeah, so, all right, yeah. So I hope you understand. Yeah, all right, yeah, all right, let's continue. So tournament method. All right. Now we run this, sports games, tournament that way to, to find the champion. Yeah. So that's the first round. Yeah. So here I just draw some diagram to show you the basic idea. X1, yeah, first two players. Yeah, let's assume X1 is the winner. X3, X4. All right. And but the last few players, it's not easy to pair them, because some details we don't know. We don't know if there are even number of players or odd number of players, but we know running the tournament method for real world sports games, then one player just move to the next round directly, right? Yeah, a lucky player can move to the next round. Yeah. So here, we know there is a way to get to the next round, right? Yeah. So whatever it is. So here, we may not have the details. We just, after first round elimination, then players move to the next round. Okay, then keep doing things. Yeah, eventually there is a final winner, right? Yeah. Here, let me just use X1 because one player. Yeah. All right. So the tournament method, we find the champion. That's the largest element. Yeah. So this one, we know it is the max. It is max. The question, in this round, how many comparisons do we make? Yeah. How many comparisons? Yeah. Although you see here some details we cannot specify, yeah, because unknown, yeah, unknown, yeah. But even unknown, do you know at the end to get the final champion, how many comparisons do we need? Total n elements, yeah, we know. So this is for n element array. Recall our finding the maximum, that problem. Finding maximum in an array with n elements, how many comparisons do you need for the maximum? Finding the maximum. N minus 1. Here, because you get a champion, yeah? So elimination, but how to play, we don't need to know exactly, right? We don't need to know. We only need to know because it's some kind of elimination. Yeah. Each comparison, one player is gone. But at the end, n minus 1 players gone. Yeah? So n minus 1. So this round, although some details missing, yeah. So, the details here not quite clear. Yeah. But don't worry. Yeah. So we don't need to know that details. Okay? Yeah. So here we skip some details. All right. But we know this round, number of comparisons equals n minus 1. This round. All right. Yeah. All right. Then we move to the next round. Yeah. Find second largest. So largest is gone. All right. So round 2, now we need to find the second largest. All right. Now, in this second round, yeah, all right, we use this special view. Okay. All right. What are the candidates for the second largest? Candidates, okay? Yeah. All right. Some of the elements have no chance to be the second largest. So we need to eliminate those. We only consider those elements who are qualified for the second largest. All right. So here, let me use a simple example to explain. Yeah, because you need to have some visual, concrete understanding. Here, I like you to look at the X4, this special element. Is X4 qualified for the second largest? No, because X3 already beats X4, right? Yeah. X3 has a chance, but the loser, so X4, the first round, it's a loser, right? It's gone, first round. So it has no chance to be the second largest, right? So based on this observation, now we need to summarize, find that description, find some precise description for the second largest element. Here, I need to write that description. Yeah. How to characterize, how to, find the key property for the second largest. Key property, okay? Yeah, second largest. Yeah. Let me write that key property here. All right, that key property. Okay. Let me say it this way. They must be the direct losers to the max. Direct losers. Yeah. So those players, if they get eliminated by the champion, but that maximum, the champion, okay, then they are qualified for the second largest. Direct, not indirect. Okay? Yeah. We know there are all other players, if we count indirect losers, yeah, there are many indirect losers to the champion. But only those who are direct losers to the champion, they are qualified for the second largest. Yeah, because they never lost to any other player, right? They only lost to the champion. But for other players, they all win. So those players, they are qualified for the second largest, direct losers. So that's the key property. If we find this key property, so now, yeah, so then we need to count the number of candidates for the second largest. Candidates, how many candidates? How many direct losers to the max? Yeah. Count. Okay, all right. Yeah? That's not hard to count. Yeah. Because each round, each tournament round, here I say tournament round, so not our problem solving, here we have round one round, problem solving round. But here in my discussion, I use the, tournament, the first round, tournament round, then second tournament round, and so on, okay? All right. In each tournament round, there is only one direct loser to the champion, right? Yeah. Because each round, the champion can only play one game, right? So each round, there is only one direct loser to this champion, okay? Then the number of candidates for the second largest equals, so this number of candidates, this number equals to the number of rounds, right? The tournament rounds. Yeah, so we need to estimate the tournament rounds. Okay, yeah, all right. Now, this step, yeah. How to estimate the number of rounds, right? We do pairing. If there is a singleton, then that singleton need to move to the next round. Then another round pairing, a possible singleton moves to the next round. Okay, all right. But, you know, it is very hard to cover all the cases, right? All the possible cases, you know, too messy. Yeah, all right. But now we use some high-level thinking. Yeah, because think about, if n number is power of 2, then there is no singleton any round, right? So we can get a perfect pairing all the way to the final round. Yeah. Then the number of rounds, just the log base 2 of n, right? Yeah. Log base 2 of n. Yeah. That's for n is the power of 2, the perfect case. But now it's not a perfect case, the general n. General n, you know, keep doing that. We still take log base 2, but we need to take the ceiling function. Yeah? Because they move to next round, that's the ceiling way, right? We're going up. Yeah. Yeah. So the number of pairs, actually, we round it up. Yeah, not rounded it down. Okay? Yeah. So based on that understanding, we can get the number of rounds. That's this many. Ceiling function of log base 2 of n. Okay? This many candidates. Yeah. So now we figure out the total number of candidates for the second largest. All right. Then we need to find the largest element only in these candidates, right? Yeah. Other non-candidates, so we eliminate them. Yeah. Non-candidates. Now the question, next one, find the largest in these candidates. How many comparisons do we need? How many more comparisons? Yeah. Is it? Because we know the total candidate number, right? This is the total candidate number. The total candidate number minus 1, is that? Because we use finding maximum, that solution another time. Yeah. For this time, yeah, because the candidate number is this one, then minus 1. All right. That total, we need to combine first round, second round. Okay. First round n minus 1. Second round minus 1. Yeah. So the final formula n plus minus 2. So this is the final formula. Okay? Look at that. That's the solution. Okay? Yeah. That's the solution. Second largest. Yeah. Yeah. After you understand it, then when you need to find the second largest, you plug in the number into this formula. So you get a solution. Yeah. And this tournament method, this solution, yeah, actually, this is the best you can get. Yeah. This you can call optimal. You cannot do better than this. It's optimal. Yeah. The best solution. Yeah. All right, so we complete this special selection problem. Yeah. Then the next one. After this one, we need to find the third largest element. We need to use the solution of the previous one then to solve the third largest. But this one, yeah, the solution based on the previous solution may not be the best. Near best may not be the best. Yeah, so that's something I need to let you know. Yeah. Yeah, so we may not be the best solution. Okay? Yeah. Because it is harder and harder. So when you move the rank to the middle, yeah, because near the ends, that relatively easier, right? The rank number near the ends, yeah, left, right, yeah. Moving toward the middle position, then becomes harder and harder. Yeah. All right. Then very hard to get the best solution. Yeah. So here we just get the near best solution. Yeah. All right. Still 2 rounds. First round, second round. Yeah. But second round we can use the previous solution. Yeah. All right. The first round. Still tournament. Tournament method. All right. But when we apply tournament method, we apply it on the first n+1 elements. Not all elements. Okay? Yeah. Yeah. We do not use the last element. So one element. Yeah. Okay? All right. n-1. Okay? Yeah. So we leave xn out. Okay? Yeah. All right. Tournament method. All right. So let me still draw some similar diagram. But last one, n-1. Okay. Assume x1 is the final winner. Yeah. Final winner, but in this n-1 elements. Not in all n elements. Yeah, all right. But, let's count. Yeah, we need to count the number of comparisons in this round. Equals n-2, right? Total number -1. n-2 this time. All right. Then elimination step. We do elimination. All right. Let's look at x1. x1, yeah, the largest one in n minus 1 elements. So it is in top 2, right? Because the only one that could be greater than x1, that's the xn. Only xn has a chance to be larger than x1. Yeah. So x1 is in top 2. If x1 in top 2, it cannot be third largest, right? Yeah. So, yeah, x1 cannot be the third largest. So we can eliminate x1 for the second round. Okay? Yeah. So we eliminate x1 for the second round. All right. Round 2. Yeah. But in the second round, now we need to update the rank. Our original goal, find the third largest, but after we eliminate one in the top 2, x1, the original third largest becomes current second largest, right? Yeah. So we updated original third largest equals current second largest. But current second largest, can we use our previous solution? We just did. Yeah, yeah, yeah. But we need to do it carefully. You need to do some careful work. Yeah, the general formula is there, but the question, there is one important question we need to consider. All right. All right. After we remove x1, all right, there are many elements, yeah, and there are many comparisons did in the first round, right? The question is, we can reuse those comparisons in the second round, right? Yeah. Many of the comparisons are still useful for the second round. We don't want to redo it. Yeah. So we need to reuse the. So let me write this, our idea in the second round. We need to. This right. Reuse those comparisons. That x1 is not involved. How about that? Not involved. Okay? Those comparisons without x1, yeah, you know, they are still useful for the second round. We just use the results. Okay, all right. So the second round, we still do the tournament, we inherit that tournament, but we replace x1 by xn. How about that? The location originally occupied by x1, now, because we have a free one, xn, we use that last element, xn, to put it in the position of x1, filling in for the tournament. Then, just, do the comparisons. Do the comparisons with, but each one xm must be involved. Xm, because all other information is known, right? Yeah, we do not need to redo it. Only the information related to xm unknown, so we need to do comparisons. Yeah. So the next round, replace x1 by xm, x2. Okay, yeah. Then other, we do not need to redo. So, if the comparison results, we can use the older one. Okay, all right. Then, but when we do it, all right, so we put them together, but we use the formula for find the second largest formula, because our goal find this time second, finding the second largest, right? Not the largest. Okay? Yeah. But we have that formula. Okay? Right. So, but we need to find the second largest. All right. We can apply that formula. But before we apply formula, we need to do one important step. How many comparisons? Well, how many comparisons can be reused, right? We need to figure out. Yeah. We need to know how many comparisons can be reused. Yeah, that's important. Yeah.
Isn't it n-1 minus the log base 2?
Correct. Good.
Tournament round?
Right. Tournament rounds, x1 involved, right? Those comparisons. So when we eliminate x1, so all those comparisons with x1 involved, they cannot be reused. Those numbers cannot be. The remaining all can be reused, right? Yeah. So that's a good one. So now we need to calculate the total number comparison n minus 2, right? Yeah, total number comparison from n minus 2, remove those number comparisons with x1 involved. x1 involved the number of runs, right? Yeah. So the number of runs, we have this formula, seeding function, log base 2, total number of elements is n minus 1, right? Yeah. So this many comparisons can be reused. All right. Can be reused. We do not need to redo it. Okay? In other words, this many comparisons, when we apply the second largest formula, because this one there is a formula, when we apply this many comparisons, this many comparisons. Because when we can be saved, because we do not need to redo it. We just use the older result. We can save this many comparisons. Yeah. With this understanding, now we can do the final round calculation. Final round. All right. Final round. Yeah. All right. Yeah. Before final round, let's calculate. Yeah. Let's calculate the subtotal here. Okay. Yeah. Otherwise, too messy. Yeah. Calculate subtotal. Subtotal, by our formula, the total number of elements, that is n minus 1, right? Total number of elements, plus seeding function minus 2. That's our formula. But we change the number from n to n minus 1. Yeah. All right. Now we are ready to calculate the final formula. All right. Yeah. First round, yeah. Subtotal from first one, That's n minus 2, right? Yeah. The first round. Okay, all right. Then, from second round, 2 parts. Yeah, the total formula is this one, but this many from can be saved, right? So we need to, yeah. That's the total number of comparison we need to do, but in that, this many can be saved. Okay. Saved, that means we can do this many fewer whatever, yeah. Then, now we do some simplification. Okay, all right, yeah. Yeah, all right. So, all right. So, then log part is relatively easy. Okay, minus minus plus, minus minus plus. So you have 2 log. Then the non-log term, yeah, minus 2, minus 2. You see, yeah. All right. Let me write this equals n plus 2 times log base 2 of minus 1 minus 3. Okay? Yeah. All right, because this n minus 1, although n minus 1, but the n minus 2, right? Minus 2, minus 1. But the n minus 2, we can cancel this n minus 2 out because minus, right? So minus 1 left. This minus 1 left. Minus 1, we add here, minus 3. So that's why we're minus 3. Okay? Yeah. So the ceiling function log base 2 minus minus, so plus another ceiling function log base 2 of n minus 1. So that's why we have 2. Okay? All right. So this is the final formula. But this is the near best solution. We cannot say it's the best solution. Yeah. So it's near best solution. Okay? Yeah. Yeah. A little messy, yeah. Lower part, a little messy. Yeah. But, when you study, you can do it on your scratch paper carefully. Yeah. Yeah. It should be correct. Yeah. So you just write, you have more space, so you do, simplification carefully. Yeah. So you will get that number. Right. Yeah. Now, yeah. So we can test a little bit. Yeah. We can test a little bit. So let's do a simple example. Example, n equals 7. N equals 7. So given 7-element array, now I ask you to find the third largest element. Okay? Find the third largest element in 7-element array. Now you can apply this formula. Okay? Yeah. You can apply this formula. All right. Yeah. So this formula, okay? N plus 2. So n is 7. Plus 2 ceiling function log base 2 of 6, right? N minus 1 minus 3. That's the formula. Okay? All right. So 7 plus 2 times 3, right? Minus 3. Then 10. Okay? Yeah. Yeah. So here you can see there is a 10 comparison solution. We don't know if it's the best. Yeah. We can only say it's near the best. Yeah. All right. Yeah. This way we can use 10 comparisons to find the third largest element in 7. But there is a there is a small possibility if people do in a different way, it's possible to use 9 comparison. There is a hope using 9 comparisons to find third largest. But you need to try it. Yeah. Otherwise, we have, in the final, in your homework, if you see that question, at least you can find a 10 comparison solution. Okay? Yeah. If you cannot figure out 9 comparison solution, because it could be very challenging, then you have a 10 comparison solution. Okay? Yeah. Things like that. Yeah. Things like that. Yeah. All right. So we finish part C. Yeah. 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 All right. And in our final, we will have some challenging questions. The challenging questions, usually I give you find third largest. I won't give you find second largest because that formula already optimal. So, too easy. Yeah. If I give you that, I do not treat it as a challenging question. I will treat it as a basic question. Yeah. The challenging, it must be third largest or median of certain number of elements, median or third largest. Yeah. But when I give you, I may give you some partial information. Yeah. If I give you 7, for example, if I give you 7 elements, I also tell you x1 less than x2 less than x3. Okay? So you can use this condition to save a few number of comparisons. Yeah. I'll give you some condition. Yeah. So you can do better. Without any condition, then so that's that way, or try other way. But with that condition, now you can take advantage of that. So when I graded your midterm, so many students didn't use the given conditions. Quite some students, they didn't use the given condition to save a few more comparisons. That's very common. All right, so let me finish part C right here. Yeah. Now I need to jump to part D, so because I still have some time. Oh, question. Yeah. Let me check the chat message. Chat message. Right. Too big. Yeah. That big. It's hard to read. Yeah, let me just make this. Anyway, yeah. Do we encounter problems like this in real world applications or just challenging? Yeah, the question, yeah. So it may not be exact, but similar to this, okay? Yeah, because selection, I mentioned 3 types of basic question types in algorithm. Yeah. Selection problem, sorting problems, and search problems. These are 3 basic algorithm types. Yeah. So in a real world situation, yeah, so you need to find a solution, could be slightly different, the condition could be different, yeah. But you have a good chance to see, similar questions. So that's one. Another is we use these questions, yeah. So you're challenging your understanding. Another is actually not just challenging your understanding, practice your problem solving techniques. Yeah. So I can say this way. Problem solving. You need to get training in problem solving. Yeah. So these questions we also use to help you improve your problem solving skills. Yeah. Okay? Yeah. Problem solving, you need to use some thinking, right? Yeah. So, elimination, all these methods. Yeah. You need to practice using all those methods. Yeah. Yeah. Thinking. Yeah. Yeah. So here, let me make some comments before I move to the next topic. Yeah. Let me just use 2 or 3 more minutes. Yeah. Yeah. Because many students, I saw many students ask similar questions. Yeah. Like, Wojo asked here. Many students, yeah. Because I remember many years ago when I taught Tower of Hanoi problem. Yeah, then one student wrote comment on test paper. She thought people will never have the situation in the real world to use the Tower of Hanoi problem, right? Yeah. Yeah. In other words, it looks like it is useless. Why we do it here? It's useless. Yeah. So do not think in that way. So here, let me give you the justification. Yeah. Why we learn Tower of Hanoi problem? So the same problem may not occur in the real world, but the problem-solving thinking will be useful. Similar problem-solving, yeah, the recursive thinking, how to do the gapping part, how to, all those, the thinking of problem solving is useful in the real world. Yeah. Do not just restrict yourselves in the specific problems. We use the problems to learn problem solving skills, problem solving thinking. So that's valuable in the real world. Yeah? Real world, you know how to do the thinking, right? So that's valuable. Okay? Yeah. The specific problem we use to give you a chance to practice the thinking, problem solving thinking. Yeah. So that's the reason. Yeah. Yeah. So many students ask similar questions. Yeah. Yeah. All right? Yeah. So here, similar here, but here the situation is slightly different. Here we did some basic selection problems, and actually in the real world, these selection problems will be used in the real world situation. Will be used. Okay? Yeah. You will have chance to use. Yeah. So it's not like Tower of Hanoi problem. So you probably have 0 chance to use. Yeah. Tower of Hanoi problem. But this one, it's not zero. It's not 0 chance. Yeah. So you have some reasonable chance to use. Yeah. But the most important part is the solution method, the problem-solving thinking part for the solution. That is more valuable. Okay? Yeah. Yeah. So, yeah, good. Okay. So I hope you understand in that way. All right? Yeah. So not not restrictive. Oh, you can only use these ways, tournament method, elimination method. They are very general methods, right? Yeah. So not restricted to, these are a few questions. Yeah. Think about that. Okay? Yeah. All right? Yeah. Yeah. So I need to use the remaining 15 minutes. Yeah. Remaining 15 minutes, start party. Let me give you an introduction part. I try to complete this part D today. I try my best to complete part D today. Yeah, there is a chance that on Wednesday we can start module 5. All right. D.1, introduction to quicksort. From the name, we expect this sort, relatively quick. Yeah. Actually, if you compare with other sorts, other known sorts, many other known sorts, this is the best among the known sorts, quick sort. Yeah. So for that reason, we should learn this one. All right, introduction. Emphasize overall performance. Yeah. So different sorts, they have different properties. Yeah. The main property of this sort, it has the best overall performance. Yeah. Average case efficiency. Yeah. Yeah. All right. Yeah, so our same old problem, but we will do it differently. We will use a different view to understand. Yeah. Divide and conquer. But when we do divide and conquer, there are many different ways to do divide and conquer. Yeah. And in this one, we want to compare it with the merge sort. Merge sort, we also do divide and conquer. Yeah. But the focus, the focus is different. So let us compare the difference. Yeah. All right. Yeah. But this one, in order to achieve the best possible overall performance, we need to sacrifice a little bit, right? Yeah. You cannot get everything the best. So you have to sacrifice somewhere, trade-off thing. The sacrifice here, we have to tolerate poor worst-case performance. That means we cannot avoid. Okay? If you compare it with the merge sort we avoid worst case. Because for the merge sort, so later you will see for the merge sort, the worst case we control in big theta of n log n. Yeah, that means it is not bad. Yeah, we control it. Yeah, not too bad. Yeah, and this one we tolerate. So then we cannot avoid that kind of poor. So that we allow. So this means tolerate here means we allow. Poor worst case. How poor? Big theta of n squared. This poor. Okay? We allow it. Yeah. But the good thing is, although it could happen, this poor worst case could happen, but the probability for this kind of poor worst case is very small. When you take average, then, the average is very good. Yeah. So you have this bottleneck. This is the bottleneck. Yeah. So there is a bottleneck in your algorithm. Yeah. But if you run on random data, so the probability that poor worst case happens very, very small. Yeah. So you average it to all the cases, still pretty good. Yeah. All right. So that's the property. Yeah, very small, very low. Now, we change the view on divide and conquer. Yeah. So if you recall the merge sort, our divide step is very simple, right? We don't need to do much because we divide in the middle. Divide given array, right in the middle, split. So the amount of work we need to do, very little. So that's the merge sort. Yeah. But the merge step, we need to do a lot of work. When we merge two ordered array, we need to do many comparisons. Yeah. That's the merge sort. Here, we will do things differently from this merge sort. Yeah. All right. Merge sort device step, you do the minimum amount of work. Here we use big theta of 1. Yeah, very little. Right? Yeah. Conquer, recursion, combined step, you need a big theta of k. Yeah. The data size, k. Right? Yeah. Now, we want to do things the opposite way. Yeah? Opposite way. Because we want to get a different solution. Yeah. We want to make the combined step very easy. The combined step, we want to, almost nothing. Almost nothing. So big theta of 1. But you cannot get a device step also almost nothing. Then you do not need to do any meaningful work, right? It's impossible. So you have to do work somewhere. Yeah, you have to do work somewhere. So the main work you need to do is at the device step. Yeah. Yeah. So we need a big theta of k in the device step. We need a lot of work in device step. Okay. After that, yeah, because we already do a lot of work, we should enjoy the result, right? Yeah. Because the result of the device step should have some very nice property. Then later we should enjoy the nice property of the device step. How to use it? When we combine the two order array, we put together, it's done. That's the way we enjoy the result from the device step. Because when we do the, division thing, partition, we will call partition. Okay? When we do the partition, we carefully, arrange the elements to make them have some nice property. Yeah. So that, combine, put together, done. No comparison, put them together, there, sorted. Yeah. So that's the different idea, completely different idea. Yeah. All right, yeah. All right. So that's the idea for this quick sort. Yeah. So and we expect different result from the merge sort. Yeah. 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 All right. Now let's look at the details. Yeah. Now the hard part. Yeah. We need to understand for what kind of property, when we use that property, we put two ordered array together, we get the data sorted automatically. We need to understand that property first. Yeah. All right. Almost do nothing in the combined step. Yeah. So you need to imagine. Yeah. First order array A subarray ordered, second order subarray B subarray ordered. Yeah. You just copy them. Yeah. So you put them together. Yeah. You copy them into the same array. You do not need to do any rearrangements, shifts, swaps. No more work. Yeah. Put them together, they are ordered. Yeah. So we need that property. We need to understand, we need to see that property. In the partition step, we can make that happen. Yeah. So that's what we want to do here. Yeah. All right? Yeah. Here, let me use two diagrams. Use a simple diagram to show you the property. Yeah, simple property. All right. All right. So here you imagine two subarrays, A subarray, B subarray. Yeah. All right. Before conquer, they are not ordered, right? Yeah. Before conquer, yeah, you split. Yeah. But after conquer, they are ordered, right? Yeah. Conquer by recursion. Yeah. Conquer step, you don't need to worry about how to conquer. Recursion, yeah. So by recursion. So after the conquer step, both are ordered. Yeah. Yeah. Sorted? Sorted. All right. Now, you need to think about some special condition. All right. Yeah. These two ordered subarray, when we join them directly without any special work. Yeah. No more work. When you join them together, no more work. And the join array is ordered automatically. But you need some property, right? Yeah. Because you cannot without any property. You have to have some special property to get that. Okay? All right. The whole array is automatically sorted after you just join them directly without one more comparison. No more comparison. Yeah. All right. All right. So we need to know for what's that property we need. Yeah. All right. Yeah. All right. Yeah. So when combined, do nothing. All right. What condition do we need before conquer? Before conquer, there is some condition you need to have. Okay. All right. This is the condition. Yeah. All right. The values of all the elements in A subarray should be less than or equal to the value of any element in B subarray. Yeah. Or the maximum of the A subarray should be less than or equal to the minimum of B subarray. In that way, you put them together ordered, right? Yeah. That property. Yeah. The maximum of A subarray less than or equal to the minimum of B subarray. How about that? Yeah. No comparison needed. Yeah. Yeah. Just join them. Done. Yeah. So that's our target. Yeah. When we do partition, that's our goal. Yeah. Yeah. After we do the partition, although each subarray not ordered, A subarray still you need to conquer. So not ordered, B subarray not ordered, you need to conquer. Okay? But you know the maximum of the A subarray is less than or equal to the minimum of B subarray. That's the criteria you use when you do the partition. Okay? Step. Yeah. All right. Yeah. But the harder part is how to make that happen in your partition step. How do you make that happen, right? It looks like you need to do a lot of work. Yeah. To make that happen, you need to do, solve some relatively hard technical problem. Yeah. Yeah. All right? Yeah. Yeah. Now we need to study the most important step, divide step. This is the most important step. Yeah. After we study this divide step, then the remaining, by recursion, remaining, pretty straightforward. Yeah. After we know how to get an A subarray, how to get a B subarray with our targeting property, then almost done. Yeah? The whole algorithm almost done. Yep. Because we just do recursion. Okay? Divide and conquer, recursion, Yeah. Yeah. So we need to, next step, we need to put a lot of effort, understand this divide step, the partition step. Yeah. All right, let me give you a break.